exactly does a VSUF implement NAT?
A VSUF is used as a CGN service board, which does not provide interfaces. It works like this. After receiving traffic, a downstream interface board diverts it to a CGN service board, which performs NAT before sending it back. The downstream interface board then sends the traffic out. NAT traffic can be forward or reverse. Forward refers to the private to public network direction, whereas reverse is the opposite. Forward traffic is diverted to a CGN service board after matching an ACL, Access Control List-based multi-field traffic classification policy on an interface board. Once the service board performs NAT, it creates a NAT session. If subsequent packets reaching the service board match this session, they are sent to the downstream interface board. In terms of reverse traffic, after a network-side interface board receives such traffic, it searches the routing table and finds a matching UNR, User Network Route. This route is automatically generated once related NAT configuration has been performed, and the next hop is the CGN service board. So after the reverse traffic matches the UNR route, it is diverted to the CGN service board for address translation, and then sent back to the downstream interface board. As a result, a round trip is completed.
How is our understanding of this forwarding process helpful for troubleshooting?
If a fault occurs, this forwarding process enables us to systematically determine the point of origin. First, we can determine whether the fault occurs on the CGN service board or interface board. Then, we can run the relevant display commands to locate the fault.
Talk us through the overall troubleshooting process if a NAT service fault occurs.
Sure. Let's take an NE40E modular device as an example. First, we need to check whether key resources such as license, public address pool, and bandwidth resources are sufficient. If these are all sufficient, we then query alarms or logs to locate the fault. If the alarms and logs are all correct, we then check the basic configurations, including traffic diversion and route advertisement. The first step is to run the display license command to confirm whether a NAT license file exists. If not, we need to apply for the license. If a license file exists, we then check whether sufficient resources are available. If so, this check item passes. The second step is to run the display NAT address usage instance command to check whether sufficient public address pool resources are available. If resource usage is below 100%, sufficient resources are available and no action is required. If resource usage has reached 100%, we need to add some public IP addresses. Adding public IP addresses does not affect services, and we only need to run the NAT address group command in the NAT instance view and add an address section. Another key resource item is bandwidth, and we can run the display NAT statistics payload command to check whether bandwidth resources are sufficient. Both current and historical maximum bandwidth usage values are available here. We usually look at the maximum value, as the current value does not necessarily indicate peak bandwidth usage. If the historical maximum value exceeds the board processing performance, capacity expansion is required. If the bandwidth resources on the service board are insufficient, check whether a bandwidth license is configured. If so, expanding the board capacity is the only option. Otherwise, run the ActiveNAT bandwidth enhance command in the license view to configure a bandwidth license. If these key resources are all normal, we should check basic configurations, which mainly include traffic diversion and NAT instance configurations. The NAT outbound command in the NAT instance view is a particularly error-prone configuration. If this command uses an ACL, the ACL rule may not contain all private IP addresses that require NAT. NAT traffic diversion configurations also require attention, and we should check whether the ACL configuration for traffic diversion and behavior configuration are correct, and whether the traffic policy is properly bound.
Are there any fault locating methods specifically formulated for distributed NAT deployment?
There are several common causes for user login failures. One such cause is similar to that found in the centralized NAT scenario, whereby the ACL rule for NAT outbound does not contain all the required private IP addresses. Another cause is insufficient public address pool resources, which means insufficient port resources. The reported failure cause in this case is public ports failing to be allocated.
What are the typical issues encountered on a live network?
The most common issues are login failures, internet access failures, and slow internet surfing. Regarding user login failures, we've already explained the causes in distributed NAT deployment scenarios. Such issues exist only in distributed scenario. Instead, let's focus on internet access failures and slow internet surfing. For internet access failures, we need to analyze relevant packets. If a large number of packets using port 53 are found, it means the DNS server is not responding. This typically occurs when public network routes are not advertised. We can use an IP address in the public address pool to ping the external DNS domain name system server. If the ping succeeds, route advertisement is normal. If the ping fails, we should check the routes. Regarding slow internet surfing, the most likely cause is insufficient port resources. For example, 1,024 ports are allocated to a user. However, in some cases, services use more than this and are unable to obtain a port from a device. As a result, the user is unable to access the external network or experiences slow internet surfing. We can directly change the port range to resolve this issue, as this does not affect the services of users who are currently online. Newly logged in users will need to log out and log back in again after this change. This assigns more port resources to the user as the new value takes effect and resolves the slow internet surfing issue. In addition to insufficient port resources, a lack of sessions is another cause of slow internet surfing. For example, the configured port range contains 4,096 ports, but the session limit is set to 1,024, meaning a maximum of 1,024 sessions can be created for a user. Additional sessions are not allowed unless the created sessions age, and the user continues to experience slow internet surfing in this scenario. To resolve this issue, we can also directly adjust the session limit to a larger value. Generally, if session limit, port limit, and port range are all configured, the smallest value takes effect. If only one is configured, the default values of the other two must be checked. It's important to note that port range has no default value, but session limit and port limit have. The value of port range should be smaller than the default values of the other two. Otherwise, their default values must be increased.
Can Huawei routers interwork with an NMS? And what alarms does a VSUF board support?
Interworking with a third-party NMS is a basic function of Huawei routers. If a fault occurs, the routers report alarms to the third party, or Huawei NMS. For the third-party NMS, Huawei must provide the OID for the NMS to receive the alarm. Several key alarms are related to forwarding performance, session resources, threshold crossing, insufficient port resources, and public address pool resources.
Could you talk about some examples you have encountered in your work?
The first example is that no user group is configured in a domain in scenarios involving distributed CGN deployment but centralized application, which leads to traffic interruptions. What do I mean by distributed CGN deployment but centralized application? In these cases, the CGN function is deployed on the browse from which users go online, but is separated from the browse user access function. NAT requires traffic diversion from an interface board to a CGN service board. In a distributed NAT scenario, the user group command must be run in the domain view to implement the diversion, and the corresponding user group must also be specified in an ACL rule. The user group traffic that matches the ACL rule is then diverted to the CGN service board for processing. If the user group command is not configured in the domain view, traffic cannot be diverted to the CGN service board. The second example is that not all required IP addresses are specified in the ACL rule of the NAT outbound command. This issue has been explained before and often leads to user login failures. When we run a command to query the cause, the command output shows that the user fails to obtain a port, or that port allocation fails. The prompt information varies depending on the version, but conveys the same meaning: failure to allocate public IP addresses. This is the situation in distributed NAT scenarios. In the scenario we mentioned earlier involving distributed CGN deployment but centralized application, a user requesting to go online is assigned a single private IP address. A public IP address can be assigned to this user only when the user traffic arrives at the device. This is different from distributed scenarios. If a private IP address segment is missing in the NAT outbound policy, users within this private IP address segment cannot obtain public IP addresses. This is because the user's private IP addresses do not match the ACL rule in the NAT outbound policy. As a result, the device does not perform NAT for the traffic, and these users are unable to obtain the corresponding public IP addresses. To resolve this issue, the missing IP addresses must be added to the ACL rule. This operation can be performed while users are online and does not affect services. The third example is that the return traffic of some users cannot be forwarded. This issue becomes evident when the traffic of some users fails to be forwarded under the same configuration. One possible cause is that not all public address pool routes are advertised. For example, a public IP address with a 22-bit mask is configured, but only 2 public IP addresses with a 24-bit mask are advertised. Or a public address pool is configured by specifying the start and end IP addresses instead of specifying a network mask. For example, if 100 public IP addresses are configured by specifying a .1 start address and .100 end address, but only 50 or 60 routes are advertised, the return traffic matching the remaining routes cannot be forwarded. As a result, users cannot access the internet. The fourth example involves using Huawei devices to replace non-Huawei devices. When such non-Huawei devices generate public address pool routes with a 32-bit mask, a black hole route is configured to summarize these routes into a network segment route. If the public address pool on a Huawei device is configured by specifying a network mask, the address pool routes will be in the network mask format. For example, if an address with a 24-bit mask is configured for the public address pool under a NAT instance on the Huawei device, a UNR route with a 24-bit mask is generated. If a black hole route with a 24-bit mask also exists, it will be matched by return traffic, as this route is statically configured and therefore has a higher priority than the UNR route generated by the Huawei device. The return traffic is then discarded as its next hop is a black hole. To solve this problem, we only need to delete the black hole route in the system view. The fifth example involves P2P applications in games operating incorrectly, or instances where users are unable to play games properly. One possible cause is the use of 5-tuple NAT by default on Huawei devices. A 5-tuple refers to source and destination IP addresses, source and destination port numbers, and the protocol type. In some cases, the destination information used may not actually be necessary for game functions. Exactly matching 5-tuple requires all 5 items to be matched. If A accesses B, only B can respond to A, and C is not permitted. However, some games require not only B, but also C, D, E, and F to access A in such a scenario. To solve this problem, we only need to run the NAT filter mode full cone command in the NAT instance view. This action replaces 5-tuple NAT with 3-tuple NAT. Another issue occurs in dual device backup scenarios. For example, no sessions exist on the backup device, or the number of sessions on the backup device is far less than on the master device. This is because session backup is conditional. We can perform the following operations to troubleshoot this issue. First, check whether the service H ahot backup enable command is configured on the backup device. If not, sessions are not backed up. Second, check whether the sessions are in the hit state. Using TCP as an example, we need to check whether the session is established after the TCP three-way handshake is completed. If the TCP three-way handshake is not completed, the session is in the no-hit state and will not be backed up. Third, check whether the aging time is longer than 10 seconds. If only 10 seconds remain, the session is not backed up as it was about to age. Fourth, check whether the session is for a regular service, as those not for regular services are not backed up. For example, sessions relating to ICMP ping packets are not backed up, as such packets do not belong to a regular service. Finally, check whether the session is an ALG session, as these are also not backed up.